Camera's placed right this week too. Okay, welcome to what should have been last week's lecture, week 5. Um, after I'm done today's lecture content, I'm going to do a quick overview, not a review, an overview of what's on the midterm and the rules of engagement. And then I'll do I call it a stealth review where I do basically everything you guys were taught in one long supercut, so to call it, where I normalize a table of data and then I diagram it. And the table of data is brand new. I literally generated it just before the start of class, so I haven't even tried to normalize it before. So we'll see how this goes. We're gonna be yeah. I was about to go get the door. I don't know what it is about B building, but B building is so loud. Okay, so today we're gonna be talking about two topics, and my clicker is not clicking. Indexes and views. So I'm going to talk about what they're for, how they work, some examples of how to create indexes, and same thing with the views, what they are, what you use them for, some examples of what views, SQL, what they do. So the first item of topic will be indexes. So indexes are a data structure that increases a database's efficiency in accessing data. Although this is more of an SQL topic, it has to do with design, so that's why it's tacked into the end of the design lecture. Um, so indexes they exist, they're invisible to you except for their definition. You can't see what's inside the index. It's just there. Indexes aren't required. The database will function properly without them, but it can affect the performance of your database significantly. So a good analogy would be, you've been given a textbook, and if you want to look up a topic, if you've actually used a physical textbook, most of us have, and you're not sure where something is in the book, you look at the back at the index for the topic, it tells you, oh, this is on page 96. Then you flip over to 96 and you find what you're trying to read about on page 96. Indexes do something similar, as in it's a structure that tells the queries where the data is in the database to make it go faster. Just like you can use a textbook without the index, it's just going to take you longer to find it because you got to literally scan through the entire book until you find what you want. Table database would do the same thing. So it'll work without the index. Indexes just make a huge performance increase. So a few things about indexes. When you create a primary key, it's always indexed. By default, it will be indexed. You can't not index it. Foreign keys are not indexed by default. So you create a foreign key when you create a table, it's not indexed. And those can make a huge difference on your performance. Something called secondary indexes are used in commonly queried columns. For example, phone numbers or postal codes, so you can search them faster. An index is going to be unique or non-unique. A unique index means column will not have duplicate values. So it's an index that also enforces a rule. 99% of indexes outside of primary keys will be non-unique, as they just make it go faster. So to give you an idea of the importance about the foreign key one, at my old job, this was years ago, pre-COVID, because I was still in office at the time. And we started getting complaints from various people about how slow a certain function on the database got. So when somebody was generating something called a license file, there was this really big query. Like when I printed, it was a page and a half long on paper. Would run. It normally would run in a couple hundred milliseconds. It was really fast for the size of it. Suddenly it was taking 2, 3, 4, 5 seconds to run. And it's like, that was a query that was run, a couple hundred to, sometimes 1,000 times a day, depending on what was happening that day. And people were going, it's getting really slow. So I started doing some, query. I was running the query analyzer, trying to figure out what was going on. Then I realized that some of the foreign keys were not indexed. One of the other guys who had made changes to the database structure had added tables that were needed in this query. When he created them, he didn't add indexes to the foreign keys. I'm like, well, that's kind of weird. So I created the indexes. The queries went from taking 3 to 4 seconds to under 100 milliseconds. It actually went faster than even before those tables were added. I don't know why, but the whole thing just got even faster. It's just being able to look up where things are makes the database server go faster. So in the most common type of index, like let's go with that, is known as a B-tree index. B-tree, so for years I went around thinking B-tree meant binary tree. I felt so stupid. Then I thought the answer was stupid once I found out what it actually means. B stands for best. Literally best tree. It's not binary tree, it's best tree. And yes, that statement will stand up because I was corrected and I called the person out on it, and then they opened up the textbook and proved it to me. I'm like, cool. So most database servers all support B-tree indexes. MySQL is pretty much all it has is B-tree. Other database servers will have other kinds of indexes like hash indexes or H trees, or there's like a dozen kinds of indexes. But B-tree does the job for like 99% of everything. So what it does is it takes the values in the field being indexed and divides it in two, then takes that, divides that in two again, then takes that and divides that in two again, and it'll go down 4 layers max. But the tree will go really, really wide, 4 layers max. It's a bit like when you play the game, guess a number between 1 and 10. Normally, everybody starts with 5. And then the person will say higher or lower. You go lower. What's the next guess? 3. And then you go lower. Then it's 1 or 2. So then you're going to guess 1 or 2. And then you have a 50-50 chance of getting it right on the first, like on the third try. That's how B-tree indexes work. They take the data and they subdivide it. So once the query divides the tree, I've got some other slides in another course I teach where it goes into a lot more detail about indexes, but for you guys, it's not a major topic. That's why they're like 2 topics in 1 lecture. So how does the correct index get picked? So the thing is that when you run the query, you're not the one telling it what index to use. Some database server allows you to tell it, hey, use this index for this query. You can actually give it an optimizer hint. They're called optimizer hints. Oracle, Microsoft SQL Server, Postgres, they all support optimizer hints. MySQL, not so much. So what happens is it's the query planner that decides which index is going to get used. So you type in your SQL and you hit run. Or you put in your SQL in your application code and you execute the SQL statement to the database. The query planner receives the query and it goes, how can I retrieve this data for the person? And then it goes, it looks at the columns that are being used in the where and in the join clauses. So it figures out what columns are being used. And based on what it sees in those clauses, it looks at which indexes are available and tries to use the best match. Yep. Yes. I'm going to talk about that in a little bit. The query planner interacts with it. So just to finish this, because I do actually talk about that a little bit. So based on what it sees in the join and the where clauses, it determines which index to use. If it can't find a best match, as in it can't find the best case scenario, or it gets confused, it defaults to no index query, and it does a table scan. Table scan means row 1, row 2, row 3. So it reads all the records for all the tables and then does the assembly in memory. You try to avoid table scans for as much as humanly possible because that's really, really bad. Okay, rules for using indexes. There, we're going to explain a little bit of stuff. So you want to use it on larger tables. By larger tables, I'm talking, you know, like really big tables. These slides are a little out of date because computers have gotten so much faster than when these slides were created. Like I've taught this course on and off for over 10 years. The last 10 years has seen huge strides in performance on computers. So take some of this with a grain of salt. Um, so you index the primary key of each table because it's going to be indexed whether you want to or not. You index search fields, which is where your question goes into. So these are fields that are frequently found in the where clause. So, select star from customer where phone number like this or phone number is equal to this. You'd index the phone number. Or you often search by postal code or you search by city because you want to often find a, say in Ottawa, you might want to index the city column. It depends on what you do with the queries. Like there's no one size fits all. What you do is you create your database, and then as the application develops, you look at which queries get run the most, and then you try to figure out what would improve those queries. So it's a bit of an investigation thing. There's like I said, there's no set rule. You might want to index fields that get used in order by and group by. Why? Because being able to figure out where the values are will make those functions go faster. You want to index when there's more than 100 values, but not less when there's 30s. This is the one I was talking earlier about. We want to take it with a grain of salt because realistically, I've seen databases with 1,000 rows and you can't tell if there's an index or not. But anything past, even 100 rows will be improved by an index. Anything really under 100 rows, you'll never notice. Even at today, the performance difference between this laptop and the one I was using when I was teaching this 10, 12 years ago, it's not even in the same realm of performance. So, I remember when I first started teaching database at college, I had a Intel Core 2 Duo with, I had a lot of memory, 8 gigabytes of RAM, and it was a lot at the time. And the laptop was like that thick, and it weighed like 10 pounds. I still have it sitting in my closet, and I'm like, it hasn't been turned on in like 8 years, 10 years, but I still have it. I really should just recycle that. So you want to avoid indexes for fields with long values. So you don't index text fields. You don't index varchar 1000s. You're not going to get anything out of it. If a key if the key you need to index like a foreign key, you probably want to use a surrogate key instead of natural keys because it'll first spread the data more evenly in the index. And numeric indexes are a lot faster than indexes of text. I honestly couldn't tell you how it works on the inside. It's a little bit, I find it a little voodoo. Because it takes your strings and it does a hash out of the string, but somehow it still knows what's inside the string in that index. I have no idea. It's really nifty. Some database servers have limits on number of indexes or the number of bytes per indexed field. I haven't seen that in years, but there once was a time where there are limits. So it's possible we end up working somewhere where they're running some ancient database and people will go, nobody does that. In manufacturing, there's some manufacturing plants that are still running Windows 3.1. Why? Because that software only works on that machine. And every time they have to repair that computer, they have to go on eBay and find, vintage computer parts to repair it. Otherwise, they're spending millions of dollars replacing all the equipment because the computer died. It's possible we'll hit one of these databases that have a limit one of these days. Be careful with indexing anything that might have nulls. Because when the query optimizer decides to use an index, and the index is on a column that has nulls in it, it actually ignores null values. They won't come back. They just get discarded because they can't be found via the index. So don't index columns that may have nulls in it. Anything that's, so you want to index stuff that's not null. It's just better that way anyways. Okay, so, and how do you decide, like I said earlier, you start writing up your application, you create your queries, and then you'd look at what's in the joins, where clauses get used a lot, and then that's when you'll choose to index. And there's actually a few other little gotchas with indexes, but I'll bring those up in a minute. So the syntax is super easy. Create index, give it a name on, table, and then a list of columns. So create index, name index on person name. So that means we're going to index the name column in the person's table. The indexes are per table. It's not per database. The index is tied to the table. You can index multiple columns at once by putting them comma delimited. So create index client, and the IDX is your choice. It's whatever you want to. It's just free-form names, right? On client name, comma postal code. So if you happen to search often on postal code and a part of a name, this index would help with that. So you go, everybody in K2C like, or postal code like K2C %, and name like Dan %, that index would help that query. If you want to make it so it's unique, you just go create unique index instead of just create index. It's a modifier in the index command. Weird. You create the table, then you create the indexes, because the index won't be able to create against something that does not exist. Well, that's the thing. As you develop the application, you'll start seeing which queries get used a lot. And then you can look at what columns what gets added to the where clause the most, or what's used in the joins the most, and that's what you index. Usually as part of the performance tuning. So you create your application and suddenly you are going, this interface is a little sluggish. Let's go see if we can create some indexes to make things go faster. Or as people use it more, you'll start noticing certain spots are slower than others. Then you'll go investigate those queries, and from there you can determine which ones you want to index. You can just add them as you want as you go. You can even take them out too, because there's times you don't want indexes. But yeah, does that answer your question? Okay. So, for example, create index, double index on person, age, and city would help. Select star from person where age is 55 and city is equal to Seattle. However, it would not help and select star from person where city is equal to Seattle, because the index is indexing two columns at once. If you're only searching against one column, that index will not get selected because it doesn't know how to improve that query. So in this case, you might have an index of city by itself. Some people choose to do multiple indexes because the query optimizer will choose multiple indexes if it can, as opposed to having multi-column indexes. It depends on the need. There's pros and cons to both ways of doing it. Create index, age index on person age would help for an between type query, age greater than 25 and age under than 28. This index would speed that up because you find those values really, really fast in the index. It doesn't have to go through the entire table. Row 1 is age between 25 and 28. Row 2 between 25 and 28. Instead, it goes, hey, index, which rows have 25 to 28 in it? Query, and it just figures it out. No. It just exists. It's like the librarian. You go to the library and you can't find a book. You just go to ask the librarian, I can't find this book, even though it says it's supposed to be on this shelf. And the librarian goes, yeah, we moved that book recently, and they know where the book is. That's kind of what it does. It's just sitting there making things go better. So these are really useful, but with everything that's really powerful, there's risks. Query optimizer confusion. If you have many indexes involved in the query, the optimizer might say, I can't choose, because there's just too many choices. It's like when you talk to your partner or your friends or whatever, and you say, what do you want to have for supper tonight? And they go, I don't know, you choose. Okay, let's go get some Thai. No, I don't want Thai. Let's go get some shawarma. No, I don't want shawarma. Right? Because there's too many choices. They just can't make up their mind. The query optimizer can get confused that way. There's IO performance. So this is one of the biggest risks of indexes. So every time, for every index you create on a table, that involves more disk activity. So that's what I mean by IO. So we're going to insert a new row in a table. Primary key gets indexed. So you're going to write the row of data, then it's going to update the index. So for that, updating an index is something like 6 or 7 calls to the disk, right? Does the index exist? Yes. Okay, read the index, find the location of the index, add the value to the index, write the index back. Cool. Now we have another 6 indexes to do. So instead of just being, 10 IO calls, you might suddenly be doing 60 IO calls because you want lots of indexes. So the thing is that the database is not done doing the insert until it's done touching all the indexes, which slows down writes, which is why a lot of database servers use cache, like a cache disk, like a RAM disk for cache, because it'll cache the changes in memory and flush them to the disk. Or if they're on a server with a RAID array, they've got like a high-speed solid state memory cache where the values get written to the cache and then it gets written to the disks later for performance reasons. It will add a lot of disk activity. Disk activity is not your friend. On a small database that, a dozen people use, you'll never notice it. On a huge database where thousands of people are using it every minute, it's going to hurt. Another issue, not as much nowadays, because now we actually have hard drives that are measured in terabytes. Back in the day when hard drives were measured in megabytes, yes, sir, we used to have megabyte hard drives. Disk space was an issue because the data in the index has to be stored somewhere. It's going to be on the disk. And if let's say your table was occupying 25 megabytes. So back in the day, table occupied 25 megabytes. And then you generated all the indexes. And the indexes were each occupying 5 megabytes. And you have 6 indexes. So suddenly your indexes take up more room than the actual table of data. And then you're running out of disk space back in the day. Nowadays, with our terabyte drives, you don't see that as much, but our databases are significantly larger than they used to be. When I went through school, what they called a big database, like a very large database, was usually measured in hundreds of megabytes to a couple of gigabytes at most. Like I remember the student information system at the college I went to. I remember the day the system crashed because they ran out of disk space. And back then, disk space was really, really expensive for these servers. It was the database was 355 megabytes. They ran out of disk space. I mean, my computer at the time, I had a brand new computer. I bought in my 3rd year of college. Actually, the computer wasn't brand new. I bought a brand new hard drive for it. 1 gigabyte. All my friends had like 250 megabyte drives. I was the guy with the baller computer system. It was kind of entertaining at the time. So indexes use up space. Nowadays, not as important as the IO hits. But if you have like a database in the gigabytes, even in the terabyte range, suddenly the indexes are going to start getting large again, right? Like the databases that they have for CBSA for everybody who comes in and out of the country. The databases of data. So when a transport truck comes across the border full of goods from the US, I never realized how complicated the system was until I was working at Health Canada. So there's something called a bill of lading. Every day, 700 megabytes of data gets generated by the border crossings per day on a normal day. Before Christmas, it goes into the gigabytes per day. That's just the trucks coming into Canada. Then there's the trucks leaving Canada. So the trucks coming into Canada carrying stuff that's they're not supposed to have in the country, that's in this data. Because a lot of the border inspection, they don't empty out the truck, right? They take the bill of lading, they put it into the system, and later on somebody says, "Oh, this truck coming from the U.S. had something on it that's not allowed to be sold in Canada." So then they have to trace back where this truck was going from this data. So there's like real time, like 24-hour analysis of where this stuff went. But yeah, so when the databases are that big, the index disk space will start counting again. Okay, so that's indexes. Now we're going to talk about views. So views, you guys did create view in level 1. So yeah, so I go into a little more of the technical details of it instead of the whatever. I don't tend to go spend a lot of time on views because I didn't realize you guys even had views at level 1 until I taught the level 1 course a couple of years ago, and I'm like, why am I teaching this a second time? So I tend to go over it pretty quick. It's more like a review for you guys. So views are a method to abstract the underlying table structure. You can use it to store complex queries for later use. You guys have experienced that one. You could use it to hide the structure from front-end developers because you might not want the front-end developers to actually know the underlying table structure. Or maintain the representation of database structure when the structure is being changed. So nowadays, most people just think of an application as a web app, right? Even when it's not a web app, there's still just a web app somewhere listening to API calls from your application. Back in the day, when we had something called client server applications, where the client ran on the person's computer connecting to the database server and it did the work for you. Sometimes we needed to change the database structure, but we couldn't update all the applications right away. So we create views to hide the changes or to make sure the changes are still compatible with the old applications. And then we'd patch the applications and then roll them out so they're not using this name of the table. We'd rename the table to something else. But the old name would still be there for reasons. So there's two kinds of views. You guys last semester learned about virtual views. So those are used in databases, obviously. They're computed on demand, which means you select star from whatever view. It runs the underlying query right away. It's slower, but it's always up to date. There's another kind of view called materialized views. MySQL doesn't support materialized views. There's ways to do it, but it doesn't have a proper materialized view. You create another table and you copy the results of a query into the table and you query that table instead. But real materialized views have advantages because it actually respects the indexes of the parent tables and stuff. When you use the workaround for MySQL, you have to create all your indexes all over again. So which uses up room and IO disk space. So materialized views are used in data warehousing. They're pre-computed offline, which means you create your materialized view, it creates a snapshot of the data, and that's it. The data can be changing, but what's in the materialized view does not change, which means the moment it's created, it's possible it's now stale, as in the data is not up to date. There's functions to refresh. It's literally called refresh. And you can refresh materialized view, which basically runs the view again and refreshes the data in the table. It basically truncates and reloads it. What's the point of a materialized view? In large financial systems, if you're trying to collect information about trends, you don't care about what's happening this second. You care about what was sold yesterday, what was sold last month, what your totals are for the last 3 years. Well, not quite, is it takes the data and it stores it on the disk. So it actually takes up disk space. Yeah, but it just creates a spread. So in MySQL, you create a table and you copy the data into the table. So whatever would be the result of the view, you copy into the table, you do an insert into. And then if you want to refresh it, you truncate the table and you redo the insert. With the materialized views, it's a little more efficient. Database services support them. They have a bunch of underlying, you know, yeah, it creates a copy of the data. So it's always up to date at the moment it's run, but the second it's run, it's now out of date. So one of the things I worked on my old job was um, we had a system that had about 12 or 13 years of sales data in it. And they wanted to have dashboards so they could do year over year comparison, watch the trends over years, and the queries were slow. So I created materialized views that were updated once a day. So about 2 a.m., these views would kick off, refresh the views every day because the dashboards didn't care what was happening today. It only cared about what happened before today. So what happened this week? What happened this month? What happened this year? The materialized view was perfect for this because they would actually do the summaries and the tallies, and the reports would come up in seconds. Like they go, I want to see the dashboard, and bang, the graphs were there almost instantly because they're pre-computed offline. So that's the materialized views. So creating a view, you guys created views last semester, so I'm not going to spend a lot of time on this. Create view as select. So here's a view. Here's some of the, this will actually talk about some of the technical stuff happening. So create view, Seattle view as buyer, seller, product, store from person, join purchase, you know, there's our view. Our view is going to be called Seattle view. And that's an underscore view. That just don't pay attention to this dash here. It's supposed to be an underscore. I actually inherited these slides from someone else and they're pretty terrible. Later on, we can use this view like you guys did last semester. So that's not a mystery. What happens when we create, since a view is not a true table, it doesn't contain data. You guys learned about that. It basically accesses the source table to capture the data, which means if the data needs to be modified, it has to be modified at the table, not in the view. So when we query a view, a little bit more. So we have a view called Seattle view. So we want to go select name Seattle view store from the view, joining another one. What's really cool is it'll take this, somehow extract it and actually rebuild the query so that what's inside the join. So this part here gets merged into this and it builds a query, and that's what it actually runs. So the query optimizer is actually able to dissect the two queries, figure out how they fit together, reassemble it, and it runs the whole thing on the inside. So views are really powerful because it's written for about how it figures out how to use them. So how do you insert a record in a table that doesn't exist? So we have a table called employees. So we have SSN, name, department, project, salary. Create view developers as name project from employee, where, you know, they work in development. Now, if we make this insert statement insert into developers, you'll end up with null values in the SSN and the department and the salary, because the view only sees the columns that are defined in it. So if you try to insert into it, it'll try to put nulls. Then this is where why we tend to say views are not updatable, because that means if you want to make it an updatable view, you have to include every not null field in the view, which might be defeating the point of the view. You know, you're going to include primary keys, full keys, not null field. So if you're going to have to provide SSN, department, and salary, well, you might as well just insert straight into the employees table, because to be able to insert it, you might have to anyways. So creating updatable views is actually really painful, and it defeats the point of the view most of the time. At Health Canada, I had a big discussion with one of the database designers about he kept changing the database structure on something that was causing our developers to have problems. I said, why can't you just create a view that's updatable? Let us have that view and then make your changes. Then tell us what you did so we can then make the application match. And yeah, we went back and forth about this whole updatable view thing for like 2 days. He was not a fan. I'm not a fan of them either, but you know, sometimes it's either I piss off one person to make 4 people's life easier, The joys of being a team lead. Um, if you, yeah, a dude makes the change at 6 o'clock at night, doesn't tell us. Three of my four devs start at 7 a.m. Dude doesn't start till almost 9. Where they're like, the application's crashing. We can't even get it to run on our local dev environments because it's talking to the Oracle server in the back. Why? Because he made changes to the database structure that broke our queries and it caused the application to fail. And we had to fix it. But the problem is we had to wait for him to come in. So suddenly I had 3 developers sitting there doing this for 2.5 hours. So I'm like, go do training for 2 hours till we get this figured out. Anyways, that didn't piss me off at all. So how would we add the record into a view? You need to include every primary key and every not null column to the view. Some other database systems might have requirements. There is actually some information in the MySQL documentation how to do it, just so you know. I don't ever do this. You can, but you know what they say, just because you can doesn't mean you should. Okay, updating a view structure in MySQL. By the way, if you go looking at the slides already uploaded on Brightspace, this slide's name has changed. The one on Brightspace says something else. I noticed that it was badly written, and I didn't have a chance to upload it yet. So if you need to update the structure of the view, there's 2 methods. You replace the view. There's database system specific limitations. Some let you do it and some don't. Or you drop and recreate. So it's create or replace view, and then you give it the new definition. So the reason I talk about there's database system specific limitations, for a while, Postgres was notorious for this. If you want to alter the view, but the number of columns being returned changed, you have to drop it and recreate it. You can do a create or replace because it didn't like you changing the number of things being returned. It didn't care about the rest. It's only what came out of it cared about. MySQL, that just lets you do it. Because basically MySQL just drops it and recreates it anyways. It's just hiding the fact that it's doing it. They create or replace does the exact same thing. It's just one's in 2 steps, one's not. And if you want to get rid of view, if exists is always helpful. That way you don't get an error if it doesn't exist, and then you give it the name and it's gone. All right, so that brings us to the end of the material for the first half of the semester. Um, Now I'm going to go over the midterm material. I don't know why I call this midterm review, but when I took over this class a few years ago, the prof had this like 26 slide review, which basically she fast forwarded through the entire contents for the semester, which is kind of pointless. Okay, so there's your midterm. The statistics for you guys. It's 50 multiple choice questions. Closed book. 1.5 hours. And it's worth 25% of your final grade. Now, why is it 1.5 hours? Believe it or not, Ontario actually has standards for questions, for multiple choice questions and true false. So the university standard is 30 seconds per question. If you studied, it shouldn't take you more, as long as you read it, you should be able to answer it right away. The Ontario college standard used to be 55 seconds a question. Why? Because I guess college kids are dumber than university kids. I don't know. That's just what it was. Now 50 questions, and if we went from 55 to 1 minute of questions, it should be 50 minutes, right? But I give you guys about 1.5 minutes per question because historically, 80% of my students, English is not their first language. So I'm giving you guys extra buffer. It should be more than enough. And I know the test is ready to go because it's sitting in my bag. I picked it up today from the print center. So The midterm sitting right there in my bag. No. Give it to the ones that actually came to class today. Yeah, no, afraid not. This is an exam, and I will admit it. Uh, it's an old exam that I'm reusing, and I've just changed some of the questions and changed the order of some of the questions. So it's not the same exam as it was before, but it's very close to one of the ones I did. I've seen it done in under 20 minutes. Somebody blew through it in under 20 minutes. So that's about what, 15 seconds a question. Yeah, it's fine. So what's it going to cover? ER diagrams, entities, attributes, and relationships. Like what are relationships? What are attributes? That kind of thing. The 3 stages of normalization. Database design. So that includes like choosing data types, that kind of thing. Indexes and views, obviously. We just finished talking about it, so that's on there too. Okay, here's the breakdown. This is what I actually, instead of doing a formal, this is important, this is important, this is not important, I actually give you guys the breakdown of the questions, as in per topic kind of thing. ER diagrams, entities and attributes / relationships, because they basically all go together. There's roughly 13 questions. The reason you'll notice it says approximately is depending on how you want to argue about it. Some of them might be database design, or some of the database design might be more, entity attribute type questions. So they fall into both. So I counted them. I said, okay, that's pretty much what it is. Normalization, 14 questions on normalization. 18 questions on database design. So this includes like questions about choosing your data types, selecting kinds of keys, what are certain kinds of keys do, surrogate keys versus natural keys, that kind of thing. 5 questions about indexes and views. You guys already got tested on views as it is last semester, so test a whole lot on that. So there's questions about indexes. The thing that's a little bit special about this this midterm. Okay, that's the front page. Okay, but I'm going to go way back over here so the camera can't pick it up. But the last page of the test, and you guys, it's too small for you guys to see, so that's why I'm not scared showing it to you guys. There's a table of data, and there's questions here you have to answer based on that table of data. That's probably the hardest questions on the test, the last 5 questions. Yeah, the last 5 questions. Essentially, it's basically a normalization type set of questions, and you have enough white space to, if you want to actually normalize it before you try to answer the questions, you can. Realistically, most people don't even bother. They just YOLO. Well, it'd be like, oh, what would be the transitive dependency in this table of data? Or what's the partial dependency in this table of data? So that's the kind of questions you're going to have. It's multiple choice, but you have to actually understand the structure a little bit, because one of the questions will be like, is the answer 3, 4, 5, or 6? And it's not obvious. It's like depending if you understand. Could be 3, could be 4, is it 5? As long as you understand it, you're probably okay. So what should you bring to the midterm? A pen or 2. Fluids, water, coffee, tea. I tend to ask, if possible, you bring your fluids in a transparent container. I'll explain to you why in a second. Snot rags, you need to blow your nose, paper, Kleenex. Wipe your tears as needed, depending on what kind of mood you're having. Only once have I had a student leaving an exam crying, but then I hadn't seen that student the entire semester at all, not once the entire semester. So I wasn't shocked when I saw her walking out crying. And she showed up for the final exam, but I only saw her for the 2 tests. They didn't go well. So what do I ask? That you bring your fluids in a transparent container if possible, like a bottle of water. It's the same reason why you're not allowed to have a smartwatch. So if you've got a smartwatch, that's staying off. Hopefully you don't have some of those fancy and jobs from Meta, the AI glasses from Meta. that look like normal Ray-Bans, but I know what they look like because they have two little circles right here. My bot has a pair. Those are banned. So hopefully it's not your only pair of glasses. Like literally, those are banned in all tests at the school. Why? Because you can sit there and get it, take pictures of the test. Um, Phones go away, laptops go away. Just put it in your bag under your desk. I just don't want to see it. Mute your phone before you start. Um, okay. So I don't think I have any accommodations for you guys with any of you guys, so that's fine. That first one doesn't mean anything. You have to stay in the room for 30 minutes from the start. From when I say go, you have to stay here for 30 minutes, even if you finish early. And then I'm going to say arrive on time for people that like arriving late. This is not the day to be late. If you arrive after the first student leaves, you will not be allowed to write the test because there's a chance you guys had a conversation. I don't know if you had a conversation in the hall or not about the test. That's happened. So, if I can see the person walking up as the person walking out, that's fine. But if somebody walks out and then somebody else walks in 5 minutes later, this happened twice in the last year and a half to me, where I've actually had to say no to someone. Dude showed up an hour late for the exam. There's like two people left in the room. Because the exam, everybody blew through that exam. Like, I don't know what the heck. I decided I need to make a harder exam after that one. But yeah, it was his final exam, and he didn't get to write his final exam. He still had enough points to pass the course, but he went from like an A plus to like a D because he didn't show up early. And I had him the next semester, and he was there 10 minutes early. So he learned his lesson. Don't learn your lesson the hard way, please. And for all the ones that didn't come in today, if you're actually watching this recording, uh, arrive on time because from the minute I say go, you got half an hour grace period. And if you arrive late, you don't get extra time. Like it's an hour and a half from when I say go, whether you arrive half an hour late or not. C'est la vie. If other people can arrive on time, so can you. Okay, so that's the information. So anybody got questions about the midterm, about anything specific to the midterm? Like you want more detail? Yeah, I'm actually going to go through a whole demo. So that'll actually help, you know, stabilize your knowledge about normalization in a minute. I even remember to bring all my markers this time. I came prepared. Um, okay, so you want more information about normalization. Cool. I've got that. Um, okay. I've got a table of data up on the screen. That's what we're going to normalize. Um, and like last time, I'm going to start out by putting up the screen. And unlike last time, my camera's actually grabbing the board from one end to the other. I just spent like 5 minutes tweaking it earlier. So, string out of the way. Of course, I've got a column that lines right up with the center pillar, but that's okay. We're going to work with it. Okay. I'm trying to decide what's going to be the color of my primary keys. Black, blue, green. Okay. Primary keys are going to be green today. So when we look at this table of data, we have to decide one of these set of columns lets us retrieve the entire row of data so that we can be in first normal form. So first normal form, and I'm going to write the rules over here. First normal form. Um, key is defined. Let me just turn on the light here so that the camera can pick up what I write. Okay, the candidate key is defined, and there is no repeating groups of columns. Okay. Oh, right now we know that there's no repeating groups of columns because when I created the generated this data, I decided not to do that. Good. However, we haven't decided what our candidate key is, or to make it first normal form. So when we look at this, which column or which combination of columns, let's just pull back a row of data. Product ID? Yep, that's actually what it is. So order ID and product ID. Between those two columns, we can retrieve any given row as it is. So now we can say that we'd be in first normal form our 1NF. Let's see if this black marker is better than the other one. So our 1NF is because I'm going to turn off the projector in a minute. I'm just writing over top of it now, so it's there. So let's call this order. Okay. And we have order ID. You can't see it in the column, but it's actually customer name. Actually, that's customer name. Problem when you have a really good marker. Customer ID, customer name. I'm just going to abbreviate the customer thing here. City, region, product, ID, product, name, unit, price, quantity, total amount. Close that off. And now if I turn off the projector, we have our thing. And we know our order ID was our primary key, so I can get rid of this green box. And our product ID. And get rid of that green box, and then I'm going to put in my commas, separating all my columns. This is going to get fixed on their next iteration. Okay. So we have our first normal form. We've got our candidate key defined. We have no repeating groups of columns. Cool beans. 2NF. It is in 1NF because you can't be in second normal form unless you're already in first normal. That one's, by default. If you've made it this far, you already got half the rules done. And no partial dependencies. Okay. So we know this one's good. Let's go look for our partial dependencies. All right. So when we look at this stuff here, we know that the customer ID, name, and city and region are only dependent on the order ID. It has nothing to do with the product. So this, shoot, went too far, is dependent on this part of the key. Okay, the product name and the unit price is dependent on the product ID. And then let's use blue. We know that our quantity and total amount is dependent on the entire key. So what do we do with partial dependencies? We toss them. So, and how do we toss them? We create new entities out of them. So at this point, how many entities do I have? 3. There'll be 4 later, but there's 3 for now because we have orange and blue. Okay. So now we're go second normal form. Let me just draw a line across like that. Now we're going to go 2NF. All right. So we have order information. So we'll call this, we'll keep the name called orders. And in here we have order ID, customer name, no, customer ID. I keep skipping to the name for some unknown reason. Like, come on, Dan. Customer ID, customer name, customer city, and the city region. Okay. And that's our primary key. We have, yep, products, ID, and unit price. That. And then the last one, we'll call it order line. Okay, and in here we have order ID. Just rewrite that so that it's clear. Order ID. ID, quantity, and total amount. And this one's interesting. This example is interesting. In theory, you could, and realistically, in a properly designed system, you'd have it in both places, because in the order line, we price at time of sale, not. But in this case, we don't have that, so we're not going to add to it. The point of the normalization exercise is to work with what you have and not get creative. You can get creative later when you try to improve it. So we know that our order ID and product ID is our primary key, but it's also a foreign key. I guess purple will work. So now we're in second normal form. Hmm? Yeah, so these columns, these attributes only rely on part of the primary key. So therefore they're partial dependencies, and to be in second normal form, you have to get rid of the partial dependencies. And you get rid of the partial dependencies by decomposing them into smaller entities. All right, so actual fact, you know what? I'm going to go third normal form over here. It's going to be a little confusing, but it's going to give me a little more room to work. Because at one point, I'm going to erase all this so I can diagram it. So I need to have the third normal form somewhere where I'm not going to erase. All right, so 3, okay, this is the bad marker. This is the good marker. 3 NF. All right, the definition of 3 NF. Where's my green marker? We have partial dependencies, job done. We have to be in 2 NF and no transitive dependencies. Okay, well, we've already reached second NF. That's good. We don't have to think about that again. So when we look at this, we have to, no, don't want to use orange. I've already used orange. When I look at the orders here, this deal, because, okay, product name, unit price, fully dependent on the primary key. Cool. Quantity, amount, total amount, fully dependent on the primary key. Cool. Over here, the customer name is actually defined by the customer ID. But the customer ID is not part of the primary key. Therefore, this is transitive, as in C name is defined by CID, CID is defined by order ID, therefore order ID defines the customer name by that whole rule of reflection. Therefore, we have a transitive dependency because we have to transit through a non-key attribute to get to the key. So for transitive, my markers are dying. I've had these for a long time. Okay, so that's our transitive dependency. And how do we fix our transitive dependency? It could decompose it to another table. All right, so we're going to start with customers. And we have the customer ID, the customer name, customer city, and the city region. I don't know why they called it that when I generated that data, but that's good. Pardon? Then you have to keep track of all the associations between cities and provinces and regions and stuff, and it gets really, really complicated. There's, like, for example, Ottawa. How many Ottawas do you think are in North America? There's 3 in the US, 1 in Canada. Americans aren't original. And that's our primary key here. Okay. So that's not worth it because then you have to map relationships between cities and regions and cities and countries. Normally we just let the city be something somebody can type in. That's why it just lives there by itself. The region, in theory, we really should have that as a separate entity, but that wasn't given to us as a type of data. So for now, it's just we're going to keep it simple. Okay, then we have orders. And in here we have order ID and the customer ID, and that's it. And this is the primary key. And customer ID is the foreign key. I'm actually going to put up a legend down the side with all my colors so that then you guys can take pictures of the board and you'll have the color coded what all this stuff is. All right, so then we have products. Like this, which is our product ID, product name, unit price, and that's our primary key here. And our order lines is not changing either because it stays the put. So okay, time for the legend. Okay. Okay, so we got full dependency. I used good handwriting for this one. Partial dependency. Transitive. Okay, let's spell right. That's our primary key. This is our foreign key. And that's all the colors I used. Okay, there's your legend to go with it. So now if you're going to take pictures, you got all the story. I'm going to take pictures of it too so I can post it. But, you know, for those of you that want to take pictures of the board, funny because the students in the class I teach for this one, they're waiting for this lecture so they can see this demo. Because I'm not allowed to do it in their class because we're not allowed to teach. We're only allowed to help because there's profs and we can't teach something the other ones are teaching. It's just the rules. So, but you know, they actually watch my recordings from this class to catch up on their material from the other class. Okay, now where did I put my phone? Okay, this marker's good. This marker's bad. This one's still good. I think. Did I use it? Brown? Anywhere? No, I didn't use it. Okay. Orange is toast. Red is toast. Green's still good. Blue's still good. And purple's still good. Time to buy some new markers. Okay, so these are going to go in the trash. I have to buy a whole box of colored markers every couple of years because they only last so long before they just give up. Okay. Did that get delivered? Oh my god. Okay. Okay. I'm just going to come here so I can get the whole board in one go, but then I'm going to take a picture of each one independently. It's irritating that this line's right here. If the screen was more lined up, this would have looked so much better. that. And like that. Okay. Everybody's got their photographic evidence. I'm erasing this board. Oh shit, I forgot to mark off that we finished it. Oh well. Wholly unusable. Yeah, 1 year I used to say to the students, hey, I'm going to do a complete start to end demo. And they're like, cool. Then once it goes, wait a minute, you just did a full review while doing a demo, right? Because it covers all the topics for the whole semester. And it's better that way too, because it's interactive. Okay. Oh, shoot. Let me just erase what's not important. Word. Just keep it nice and clean. There we go. All right. So now we're going to take what we normalized and turn it into a conceptual diagram. So we have 4 entities. We have what I was just using. But this one is the bad one. This is the good one. Okay. Customers. We have. I'm actually going to go with the 2 parent tables that don't have any that don't have any parents, like the 2 tables that don't have any foreign keys in them first, because they're going to be at the top. So we go products. Then we have orders. And then we have order lines. Okay, here's 4 entities. Cool. All right. So on the customers, we have customer ID, and we know that's the primary key because we identified it as being a primary key. We have a customer name, customer city, and then the city region. Okay, that's our attributes here. This one has order ID. I'm actually going to include customer ID. Normally you don't do the foreign keys, but I'll include just for you guys to get the full transition of the process here. ID. Pardon my terrible handwriting. We have product ID. ID, which we know that's the primary key. And we have the product name. And a unit price like this. And then on order lines, we have the order ID, the product ID, the quantity, and the total amount. It's actually a derived attribute because it's unit price times quantity gives you a total amount. So this is actually the first time I've actually had one of these that had a transitive, a derived attribute included for the ride. You know, I thought that was kind of fun. When I saw it, I'm like, that's perfect. And at the same time, we know that the product ID, let me just do my underlines in green so I can stay consistent with the legend over there. Okay. Okay. Primary key, 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 and this is also a foreign key. Okay. So far so good. We've got our entities and their attributes up. Now we got to do our relationships. Okay. So we know there's a relationship here. We know there's one here. I'm going to draw my diamonds in now, like such. So each customer can have multiple orders. Since and realistically, each order can only have one customer ID because it's an attribute. So it would go like this. Technically optional. Now, this is where it gets a little decision-making time. Do we decide that the customer ID is actually participating in the key or not? You can choose or not, right? But you can still choose to make it mandatory, even if it's not part of the key. So we can say that we can't place an order unless we have a customer. So a customer may not have any orders yet because in theory you could have registered a customer and they haven't bought anything yet, just like you can sign and not buy anything right away. And then the order, on the other hand, each order belongs to one and only one customer, and it must belong to a customer. All right, now we have a relationship here, and we have a relationship here. Okay, each order can have multiple order lines, and this ends up being an identifying because the foreign key participates in the primary key. So mandatory. In theory, you can't have an order unless there's something in the order line, so it's mandatory that way. And this one here is also identifying because we said it belongs to the primary key. So this one's like this. This one goes like this, right? The order line cannot, actually, no, that one's wrong. It's optional because you can have products that have never been ordered. And in the end, because the primary key is also made up of the foreign keys, it's a weak entity, which means we have to, it's the double box that goes around it. Okay, so this is the diagram for that normalization. Take this when you take out your cameras and you take a second picture. So you don't lose track of this stuff. And I'll be taking a picture too. Okay. The lights in here are really terrible. Man, I'm looking at him all zipped up and I'm sweating. I'm looking at death. He's like zipped up like it's like 20 below zero. Oh, right. Now we're going to do the physical diagram. And all this is going away now. Okay. So physical diagram time. We're going to start with the customers. We're going to lay our stuff out the exact same way as it is here. Except this time, we're going to do the physical style. Customers. And we have the customer ID. I'm actually going to drop the prefixes now because now they're self-contained. It makes sense to drop them. City, region, like such. Okay. You noticed I didn't close off my table yet. All right. So customer ID, it's probably an integer. So we want to say it's an int. Yep, and I'm going to do that after. So name as a varchar. Who knows? Realistically, we don't know what language these names are in. So we can go 75 to give ourselves a bit of wiggle room. City, varchar 50, because that's usually pretty safe. And the region, we have to decide, are we doing the ISO codes? Are we doing full names? We're going to do the ISO codes, which is 3, 2, sometimes 3, because some countries just want to be special and they need a third. So this will be I'm actually going to do car 3, just so we have something a little different, because it's always going to use up 3. Even if it's just ON, it had it. So it's always 3, but it's fine. Okay, so this is our primary key. Hey, it not that I've seen. The ISO standard is usually 2 to 3. Um, there's 2 African countries that I've seen that have 3. I don't know why, because realistically 2 would have been fine anyways. Because the ISO code's unique to the country, not to the world. So ON can be ON in 5 different countries. Somebody decided they needed a third letter just because they're special. I'm sure there's a reason. I'm being a bit facetious. I'm sure there's a reason why they went that way, but you know. All right, so now we're gonna do products. We have our product ID, name, and unit price. Now I'm not following my own rules about being consistent with my naming conventions here, because my brain doesn't tend to write all the time in either uppercase or lowercase. Everything should be either uppercase, lowercase, or mixed case, but consistent. This is not consistent at all. Okay, the product ID is probably an integer. The name's probably a varchar of some sort. 50 is probably more than enough. And the unit price is probably a decimal or numeric. So I'm going to go with numeric because that's the more common way of calling it. 10 comma 2 because we really don't know what they're selling. Okay, and this is also our primary key, like this. Now we can close off our table, like such. 2 tables done. Now we got orders. This one's pretty straightforward. We got order ID and the customer ID. They're both going to be ints. This is our primary key. And this one's a foreign key. And last but not least is order lines. All right. And in here we have order ID, which is an int. We have the product ID, which is also an int. Quantity, probably an int. Derived. When it's derived, it doesn't show up to the physical diagram unless you have a good reason. A derived attribute, when you take a derived attribute from conceptual diagram, when you create the physical diagram, you don't create it unless you have a valid reason why. So if you expect millions of rows of data, that's a valid reason why. But in this case, it's derived. When we do the final physical diagram, we discard the derived attribute. So we literally, our table goes like this. It's one of the few times where you get to just get rid of something. Okay, so shoot, I closed my box a little too early. This is our PK. There's also our foreign key, like that. And all we have left to do is draw our relationships, but that's not hard because we already know what they are. We just have to redraw them without the diamonds. We go, oop, voila. That's literally everything you just learned this semester all in one go. So far this semester. It's picture time again. Say cheese. Okay, I'm gonna take a picture of that too, because I'm gonna post it all tonight or tomorrow. Okay, done. Okay, that's the normalization to diagram demo. So that covers lectures 2, 3, 4, and some of lecture 1 when we talk about entities and attributes. The only thing we didn't talk about was indexes and views. Now, if we want to talk about indexes, in theory, we could bring in the concept of indexes in here really quick. What in here would be indexed? This one would be indexed. These guys would be indexed because they're part of the primary key, but they're also a foreign key. This guy would be indexed, and since this is a foreign key, we probably want to index that one, and this one would get indexed. In theory, if we're searching for customers by city, we'd want to index the city. So those are some of the columns we could index if we wanted. Like this table structure is so simple that there's no point indexing any of it because it's not a really realistic, it's, you know. So you should, the primary keys are always indexed. So out of here, there's 1, 2, 3, 4, 5 that would be, sorry, there'd be 4. 1 index, 2 index, 3 index. This would actually be a single index, but there's 2 columns in it. So there's 4 indexes that are mandatory. You should always index foreign keys. I didn't bother put it over here again because these ones are already being indexed. So this is a foreign key, so we want to index this. So the only one in here really that's optional would be the city, but it's something that we might search on regularly, or we might want to index the name instead of the city so that we can do partial string matches. Like operators are, the performance improves on an index for like operators. But yeah, that's the ones if you wanted to index anything. These are the concepts you'll see during the exam. Like you won't see, like there won't be a complete diagram. There's going to be like, oh, here's a symbol for, you know, a crow's foot symbol, like what does this part of the crow's foot mean? You're given 4 choices, or you might see a double diamond or a double box, and it's going to say, what's this? It's not a hands-on test at all. There was talk about putting in a practical assessment this semester for the first half, and I'm like, they'd have to write both tests in one day. Not cool. So thankfully they already said no, so it didn't happen. But yeah, so there's the test is going to be multiple choice about, you have this, or you're trying to pick the data type for this kind of field. Which one makes sense? Some of these questions are, do you understand what's being asked? It's not, did you memorize this by rote? Like some of it is, I mean, you've memorized your symbols, but some of it is, hey, Joe Bob is, creating a physical diagram and he wants to store a phone number. What data type would he pick? Then you've got 4 choices to pick from. That's the kind of questions you're going to see. So, and the questions that have been vetted. Let me just hit the stop button here.